replicate Chuka's experiment by asking us to stand up, so we know what direction to take. So can we please stand up? Now, if you have never written a machine learning model in TensorFlow, please sit down. Okay, we're all standing. So, failed experiment. So there's a reason for this. Please sit down. And that's because the session is quite technical, and we have the option of splitting it into. We don't have to complete everything today, so we can get started. So, hands up if you know what TensorFlow is. Okay. Well, we're getting somewhere. Hands up if you know what machine learning is. Okay, a bit further. But how much experience, for some of the people who raise their hand, how much experience do you have with machine learning?
Code lab, recently starting off. So just as far as I'm concerned, just trying to understand the algorithm, LCA,
Okay.
CLC.
Okay. Anybody else wants to tell us what experience you have?
No, you're just scratching on the surface.
Just scratching on the surface. Okay. So interestingly, I was going to talk about putting models into production because we're in Lagos, and we naturally assume that everybody's already doing it. They're just not putting it into production, right? Because Lagos is Lagos. If you're not doing it in Lagos, you're not doing it anywhere else. However, I think we need to start from what machine learning is, first of all, what models are, before we get around to talking about putting them into production. So this talk, or this session was supposed to be about TensorFlow. But before we get to TensorFlow, let's even talk about what machine learning is, why you use TensorFlow, and then talk about a few other things. Now, machine learning itself is a branch of computing. So we're all used to writing code. We looked at orchestration and putting code into production. But the type of code that we put into production right now is code that we program with specific rules. So for instance, if you have a web application and you click on a button, there's a rule that is programmed there. So you listen for an event and then you take an action. So there's a rule. If you fill in a form, one example of rules, for instance, is when we say, is this field provided or is it missing? If it's missing, do something. This checkbox, has the person confirmed that he has read the terms and conditions or not? So those are rules, and we're used to rule-based programming. However, it turns out that there are some types of tasks that require so many rules that it's really difficult to program those types of rules. And one basic example is, how do you tell the computer to differentiate between a picture of a male person and a picture of a female person? Where do you start from? Do you say if there's long hair, it's female, and if there isn't long hair, then it's male? Well, it just so happens that in some countries, males have long hair. In some countries, females have short hair. What else do you do? Do you say if there's a piercing in the ear, then it's female? Well, that's not a hard and fast rule. So how exactly do you tell that this is male and this is female? And just in case we think that that's a difficult task and we're being unfair, you can start with something simpler. How do you tell the difference between an apple and an orange? Do you start with the color? Do you start with the shape? Do you start with the size? What exactly do do you do? How many rules do you need to write to say if these conditions are met, then it's an apple, and if these conditions are met, it's an orange? So that's where machine learning comes in. What machine learning does is it works with examples. So instead of writing rules, you provide examples, and then the computer takes a look at those examples and it figures out what it needs to do. That's a high-level explanation. But basically, if you want to teach a computer how to tell the difference between apples and oranges, you get lots and lots and lots of pictures of apples and lots and lots and lots of pictures of oranges. And after a while, the computer starts to tell what the major features are of apples and what the major features are of oranges. And then it comes up with its own, we could call them rules, but we call them weights. So it comes up with a mathematical equation that it learns to apply to this particular task. So machine learning is task specific. You don't just have machine learning models that do anything that you want them to do. You have to go out and build a model that is specific to the task. So if you want to tell the difference between apples and oranges, you build a model for that. If you want to tell the difference between different types of clouds, you build another model. If you want to tell the difference between different types of bananas, you build another model. Now, these models themselves are mathematical in nature. They involve a bunch of numerical tasks. And so libraries have been developed that help with these tasks, these mathematical tasks. And TensorFlow is one of them. So TensorFlow itself is called a numerical computation library. And what that means is it helps you speed up your task of carrying out all of these numerical computations to arrive at whatever weights are optimal for your particular problem. Now, in TensorFlow, there are different ways of writing these models, these machine learning models. There are low-level approaches for people who are in research, and there are high-level approaches for people who are in engineering. And in these high-level approaches, we then have two APIs, what we call application programming interfaces. So you've probably all done some web application, and anytime you need to talk to something outside of your core, what you do is you call an API. So in the same vein, in TensorFlow, we have high-level APIs. And these high-level APIs are generally categorized into two based on how you write them. They're actually very different in the ways that you write them. So one API is called Keras, and the other API is called the Estimator API. So in this talk, we're going to be looking at the Estimator API. And the Estimator API tries to simplify the task that you carry out. So you don't actually end up writing mathematics or anything like that. The same thing with Keras. Instead, you're given certain estimators called, they're canned estimators, meaning that they're ready to ship out. So you start by saying, I would like to carry out a certain task. And then you find an estimator that is suitable to that task that you would like to carry out. Now in machine learning, we have supervised machine learning and unsupervised machine learning. With supervised machine learning, you try to carry out a task where the examples that you give to the computer have what we call labels, meaning that you have the answers at the end. So it's kind of like saying, you're getting ready for an exam, these are past questions that have come out in that exam, and these are answers to those questions. Now, in supervised learning, we also break it down into two. We have classification and regression. And that's important to understand. So classification is basically saying what category would you put this thing into. So again, in the apples versus oranges task, you would provide examples and you'd say this particular example is an apple. And then you provide another example and you'd say this particular example is an orange. But we also have regression tasks. And in regression tasks, what you try to do is you try to predict a continuous numerical variable. An example of that is trying to predict temperature. So if you're trying to predict temperature or you're trying to predict humidity, then you're going to be predicting a number, and that's a regression task. Understanding those two is important because when you make use of an estimator, you're going to be making use of either a regressor or a classifier, and that's why they're listed that way. So if the task that you'd like the computer to carry out is to basically say, put these things in a category, then what you need is a classifier. But if what you're trying to do is, say, predict a continuous numerical variable, then what you need is a regressor. Now, the estimators themselves also provide different types of classes. So we have linear classes, we have DNN classes, and then we have combined classes. Linear classes are what we call shallow, meaning that when they're implemented as a neural network, you have only one layer with as many neurons as are required. DNN, on the other hand, implements a deep neural network. So if, at least even if you've been scratching on the surface of machine learning, you'll know that we have deep neural networks and then we have simple classifiers or linear classifiers and regressors. So we have linear regression, we have logistic regression. So this is actually linear regression, this is logistic regression, and then this is a deep neural network. And when you implement a deep neural network, you can implement it either for regression or for classification. And then it's also possible to combine a linear regressor with a deep neural network regressor based on certain characteristics. So the linear classes, for instance, are optimized for dealing with sparse data, meaning you have a bunch of features, but they're not always available. So sometimes those features are set to 0. Linear models can deal with those quite well. Deep neural network models, on the other hand, require every feature to be there, or at least a majority of those features to be there. So they're what we call dense models. Linear combined models let you have sparse on the one hand and dense on the other hand, and you can merge both of them, and that ideally improves your accuracy. So basically, you have canned estimators that will let you do linear regression and logistic regression, and then you can have deep neural networks, and then you can combine both in combine classifiers, and then you can build custom models if you need to. So if you have some requirement that doesn't meet any of these earlier ones, you can use an estimator. So as opposed to a linear regressor, linear classifier, you can just have estimator, and it's going to require a model function. But then the reason why all of these are together is that they have a similar signature. So whichever of them you instantiate, you have the same behavior. And of course, that is what gives you an API. Now, if you happen to be using an estimator, then to build a model, what you need to do is you need to import data. So remember that we said machine learning is really about showing examples and then learning from those examples. So those examples will come in a file that you need to import. At the beginning, at the early stages, typically your data will come as CSV, unless you're dealing with images, in which case they'll come as image files. So you'll need to import your data, and then when you're done importing your data, you need to do a bit of engineering, and it's called feature engineering. So you have feature columns that you create out of your data, and this is compressed. If you were to read something like the machine learning crash course, you'll have this expanded out for you. But basically, at the end of this operation, you have a list of feature columns. So this code is Python, and this is what we call the list comprehension. So basically, compressed it, and so this is like a list of the names of the columns in your data, and then we use a list comprehension to generate our feature columns. Now, estimators require input functions. So when you build models, there's a training phase, there's an evaluation phase, and then there's an inference phase, which is where you put the model into production, you start using the model. So for the training phase, there's a training input function, which you need to define. And again, this is compressed, but this is like one way of defining an input function. Like this is like the simplest way of defining an input function. So you have your training input function, you have your validation input function for evaluation, because as you train the model, you need to check whether the accuracy is getting better or not, and that's what the validation input function does. And then if you decide to adopt your model, then you're going to need your prediction input function, which is what is used for inference. And then once you have your input functions, your feature columns, you can then create an estimator using something like this. So recall, you can actually change this. So this can be linear regressor, linear classifier, DNN regressor, or any other type of estimator. Once you're done creating your estimator, you can go ahead and train it, and you train it by passing it a training input function, which is what we represent here. And then you can go ahead and carry out evaluation to see whether the model meets certain baseline requirements. And of course, if it meets your requirements, you can put the model into use by running inference, which we call prediction. And you do that by simply calling model to predict. So it's sort of pretty straightforward. Model.train, model.evaluate, and model.predict. Now, all of this works if you're in a research environment, if you're prototyping, but it doesn't work if you have that kind of environment that Chuka just finished talking about. So you have some 200,000 users, and for every time that they do something, you need to call a machine learning model and predict something. How do you do that in production? The code that we just saw doesn't work in production. You can't put it into production. So in order to put it into production, there's something called a serving input function that needs to come into the equation. And that serving is actually the keyword. And that's because the Google Cloud Machine Learning Engine is an implementation of something called TensorFlow Serving that is notoriously difficult to set up. It's probably as difficult as setting up Kubernetes on your own. Yeah, because it's so difficult that there's a Kubernetes version of it which is supposed to be easier than setting it up directly. So you need a serving input function. Now, along with the serving input function, you need a training specification, training spec, you need an evaluation spec, and you need an exporter. And then you need to define a train and evaluate function. So what the train and evaluate function will do is it will combine your training step and your evaluation step, which we saw prior to now. So if we take the previous code that we had, what we need to do is just add new functions to make it possible. So first of all, we need to implement our serving input function. So we'll define the function, and here we need feature placeholders, we need our features, the same features that we defined the first time, they come in here. And then our serving input function will return something called a serving input receiver. And when it does that, it will return our features as well as our feature placeholders. And then we need to define our training spec. And our training spec will simply take our input function and return it. And we also have the option of defining something called max steps, which is how long do we want to train this model for? How many times do we want to go over our data before we're convinced that our model has learned something new? We also need to define an evaluation spec in which we give it the evaluation input function. When we do an evaluation, we only go over the data once, but the data is even completely different. But we go over it once, and we can specify how much time we want to allow for the model to train before we start evaluation. So that's what our start delay seconds is. Our throttle seconds is saying how much time do we want to give in between training before we evaluate the model. So you don't want to just keep evaluating the model every second or something. You want to give it some time. In this case, we're giving it 10 seconds. Now 10 seconds is a lot of time because when you carry out this training, you have the option of carrying out the training on Google Cloud Machine Learning Engine, that's on GCP itself. And what it does is it distributes the load. So you're able to ask for certain types of compute engines, in this case virtual machines, you're able to ask for different types. And that will determine how much compute power you get. And then we need to define something called an exporter. And what the exporter does is it gives us a saved model at the end of the day, which you're able to upload to Google Cloud Storage, and then from there create your deployment and point it at Google Cloud Storage. And the exporter just takes two things: the name of a folder and then the name of a serving input function, which we specify. And then we define train and evaluate as a function. And what it does here is it will combine our training step and our validation step. So again, here we define our estimator, and it could be anything within the linear regressor. We specify a model directory, which is where our saved model should be stored. And this can be passed in as a parameter. But more importantly, this doesn't need to be stored on the same computer where you're training. This can be stored on Google Cloud Storage. And then we need to specify our feature columns for the estimator. Prior to now, have defined a training spec, an exporter, an evaluation spec, and then what we do at the end of the function is we call TF estimator train and evaluate, and then we pass in the estimator that we just created up here, and passing training spec which we define, the evaluation spec which we define. And once we're done, all we need to do is just call that function, just train and evaluate. And because we specified an output directory, that saved model will get put into the output directory at the end of model training. Now, if you run that on a local machine, then you just need to go to the folder that you specified, and in that folder you find your exporter, and there's a folder that you find in there which will just have a random set of numbers in there for the name, because you can run training multiple times and it will just generate new folders whenever it's done training. And in there you should find, amongst other things, you should find your saved model, and you should find a bunch of variables. Now, if you train locally, what you need to do is move to the cloud. So you can use a command line to move that to the cloud using gsutil. You need to make a bucket to store the entire folder. That's an example of it. You command line for making a bucket, and then for copying everything in that exporter folder into the bucket that you created online. And if you like to point and click, you can always just go to Google Cloud Storage, click on Create Bucket, and fill in whatever you need to fill in. And once you have a bucket, you're able to do upload files or upload folder. The problem with this is usually those folders are large, so if you don't have really good internet, then doing it this way might not be the best thing, but you can still do it this way. And once you have it on Google Cloud Storage, you can then go ahead and deploy a model. Again, you can do deployment using CLI, which is easy. You don't need to cram this, for instance. It's there in the docs, it's here on the slides. This is actually correct. So the first thing you do is create a machine learning engine model. This is the command for that. You give the model a name, you specify the region where you want it created. So if you've ever used GCP, you'll be conversant with the notion of regions and zones on GCP. Regions are just important for how quickly people can access the model after you deploy it, because there are hops. If your clients are in Nigeria, they have to hop to Europe first of all, whether Germany or something, and then if your data is not in Germany, they have to hop over to the US. And once you've created a model, you can then deploy versions. So that saved model that you exported is actually a version. And so you can create a version, and you can specify the name of the model version. You can specify the model name, which is the name of the model that you created here prior. So if this is like a version 2, you don't need to do this. You just run this and give the model a different version. Origin says pick up the folder from this place, and this place needs to be Google Cloud Storage, because that is the fastest place where anything can be picked up from. And it doesn't copy, which is really why we put things in GCS. If you've ever used Google Cloud Storage and you try to copy files from one bucket to another bucket, you'll find out that Google Cloud Storage was invented by people that don't like other people going out to make coffee. Because traditionally, you just say, I'm going to make coffee, I'm copying files, right? And then you come back tomorrow, and the files are still copied. Right? And so these guys just said, you know what, enough of this coffee drinking, right? So like, you want to copy, I don't know, a terabyte, you hit the command, before you can get the coffee tin, it's done copying. So it doesn't copy it, it just points at it. You need to specify a runtime version, which is what version of TensorFlow did you use to build this model. You also need to specify a Python version, because like everything else in computing, we like versions and versions and versions. And we never duplicate anything, so it needs to know for its own sanity. And then most people have more than one project on GCP, so you need to specify what project. Project is actually where all the billing goes. So yeah, we organize things in projects, but really that what account gets billed for hosting all of this data and stuff. And so you need to specify the project ID. And it's the same thing even when you're making buckets and stuff, you need to specify project ID. But the good thing with buckets is that they are unique. So once you create a bucket, no other person can create that bucket name. So when you copy to a bucket, you don't need to specify a project, like it's unique. Once you just say GCS : and the bucket name, it knows where to find it. Whether or not you have permission to access it is another thing. And again, whatever we do with all of that beautiful looking code, you can always do online. So you can always go to GCP, go to the navigation menu, scroll to the bottom, you have your Cloud Machine Learning Engine section, and create a model. Specify a model name, give it a description, and you have a model. And once you have a model, you can then create a new version. So as you can see in this example, I already have one version deployed, and I can add a second version, and I can say new version, and fill in on the form the same details that I would have passed in online. And that's it. you are then able to use your model. Of course, how do you use the model? So there's something called OAuth Playground, and what OAuth Playground will do is from a browser, you're able to get credentials to use HTTPS or to use Post or something, so that you can use Postman to test APIs. Because once you do this deployment, you actually have an API. So all of this stress is so that web devs, Android devs, and every other person who does not like stress can call the API endpoint. And so this is what OAuth Playground looks like. So step one, you need to select and authorize an API. There are all sorts of APIs, but you can see here we have Cloud Machine Learning Engine version 1. Once you select that, you can then say, it will open up, and then you can choose the only thing that is there really, and say authorize APIs. It will then open up an interface for you to provide authentication and then to give you credentials. Another alternative is to just use command line and say gcloud ML engine predict, and specify your model name, specify your version name, and specify something called the JSON instance. And JSON instance is just a JSON file that encapsulates the data that you want to send to it for it to run inference on. And that's it really about putting TensorFlow models into production. So even if you haven't worked with TensorFlow models, save the slides. When you start working with TensorFlow models, you'll need the same slides to put them into production. Thank you. I'll take any questions.
Okay,
Sure.
so you can start.